and welcome to college algebra. I don't know what chapter it is anymore. In this video we're going to talk about and sort of give you an introduction to functions, and in some editions of Julie Miller's intermediate algebra book, this information is in chapter 3 section 2. In other editions it is in chapter 2 section 6. So just be careful depending on which edition of the book you're using. Make sure it matches up with the correct homework assignments. And now let's talk about functions. So a function is the definition of a function. A function is a very specific type of relation, actually. So we say that y is a function of x. It says in this first yellow box, if for each element x in the domain there is exactly one value of y in the range. And that sounds good, but let's sort of see some visual representations of that. In 1a, we see that the 4 is being mapped to a 1, and 6 goes to 3, and 8 goes to 4, and 10 goes to 5. Is that a function? It is, because, said another way, each one of those x values in the domain is only being used once. In the second example, b, we see that the number 6 in the domain is mapping to two different range values. And that's fine for a relation, but when it comes to talking about a function, that would disqualify this relation from being a function. So each x value can only be used once. In part C, we see that the number 5 as an x value is being used twice. It's mapping to two different, y values, and that would disqualify it from being a function also. So in these three illustrations, option A is the only one that represents a relation that's a function. Another way that we saw in the previous section that functions are depicted is by plotting points, and then we went one step further and we actually looked at some graphs. We saw a circle and a parabola, and so here let's look at some more graphs. And what we're being, slide that down a little. What we're seeing here is a test called the vertical line test. And the vertical line test can be used when you're looking at a graph and you're trying to determine, is this graph the graph of a function? So let's see if we can use the vertical line test, which says that, how do they phrase it? The graph defines y as a function of x if no vertical line intersects the graph in more than one point. Let's actually go to option B first, because this one fails big time. So let me phrase the vertical line test slightly differently. If it's possible to draw a vertical line and intersect your graph at more than one point, then the graph is not the graph of a function. Here's why that works. Because if I draw a vertical line at x equals -6, for example, you'll see that that vertical line crosses my graph at 2 points. It crosses here and it crosses here. Okay, that's nice. The vertical line test crosses at more than 1 point, therefore not a function. Why is it not a function again? Just because I can draw this vertical line? Well, what's the x coordinate of this point? And then, oh, actually I think this is at -7. So the x coordinate here is -7 and the y coordinate is approximately 2. And here, below that, this point also has an x coordinate of -7 and its corresponding y value is approximately -2. So here you're seeing a visual representation of an x value that's mapping to two different y values. A repeated use of an x value disqualifies the relation or the graph from being a function. So therefore, this graph is not the graph of a function. Let's apply the vertical line test to this graph. Is it possible to draw a vertical line that intersects this curve at more than one point? Only intersects at one point, only intersects at one point, 1 point, 1 point, 1 point, 1 point. I think we're safe on this one. I don't think it's possible to intersect our graph at more than 1 point. Just looking at the curve, do you see any points on this curve that share the same x value? And the answer is no. There are no repeated uses of an x value here, so this graph is the graph of a function. Let's look at one more example. So this is a very unusual looking graph. It has a specific starting point that includes an x value of -2, but again, I don't see any points on this straight line nor the curved part of it. There are no points on this graph that have the same x coordinate. Again, vertical line only crosses once, a vertical line only crosses it once, and so on. So we can safely say that this graph is the graph of a function. We won't always be given a mapping like our first three examples, nor a table of values, nor will we necessarily be given the graph of what may or may not be a function. We might be given an equation, and very often in the algebra that we've seen so far in our life, we see our equations written as y=equals equations. They don't always appear that way. Sometimes, instead of saying y=, we see this notation right here, which is called function notation. And what this says, what this equation says, is f of x equals 6x minus 3. This is a function that has a name. This particular function is named f. I could just as easily have called this function g of x equals 6x minus 3. This is the name of the function, and this is where we have the opportunity to plug in either a number or another variable or an expression. Myriad things could be plugged in place of the x. What I don't want you to think is that this says f times x or g times x. It doesn't say that. If you have a digital camera that you can put a memory card into, think of this x value, this position right here, as the place where you put the memory card in. When you look at your camera, you don't say, oh, this is camera times memory card slot, right? That's not, you would never say that. And it's the same here, okay? This is just an opportunity, a place for us to put in an input value. The values that we're going to plug into our function will be coming from the domain. So input values are domain values. And then the result of doing the arithmetic, like multiplying by 6 and then subtracting 3, the result of doing that arithmetic will give us an output value, and the output value will be what we usually think of as a y coordinate, and that's also going to be a member of the range. So our input values are x values, and our output values, the results, are range values. So here we're being given a function, 2x squared minus 3x plus 1, and that is our a function called f of x. And part A says, what is f of -1? And you'll notice that the x value up here has changed into a -1. And since we've changed that x value to a -1, that tells us to change this x value to a -1 and this x value to a -1. And I recommend that when you're changing those x's to whatever it is that you have to change them to, whether it's a -1, or if it's a 0, or if it's a fraction, or a decimal, or a picture of a Christmas tree, I don't care what it is, I would put your new value in parentheses. Let's try this one. F of -1 equals 2 times, and then here's my -1 in parentheses, squared. So you're seeing this is coming down here, minus 3 times our new x value of -1 plus 1. So again, this x changed to a -1, therefore this x and this x must change to a -1, and there they are. From there, it's arithmetic. I like having this -1 in parentheses because it reminds me that when I go to square it, it should be -1 times -1. Can you imagine what this would look like without parentheses? I think it's going to be very confusing. Let's just go in and erase. There we go. And that looks like 2 minus 1 squared. All right, and that's not what it is at all. It's not subtraction, it's multiplication. So those parentheses, again, very important. -1 squared is -1 times -1, which is +1, times 2 is +2. And then here we've got minus 3 times -1. So the double negative there turns that into a +3, and then a +1 at the end, and we get an answer of 6. Therefore, f of -1 equals 6. If we were going to plot this point on the xy coordinate plane, we would plot the point -1, 6. Input, output. Let's try f of 0. This is equal to 2 times 0 squared minus 3 times 0 plus 1. 2 times 0 is 0, minus 3 times 0 means we're subtracting a 0 plus 1. Boy, that's nice. When you plug in a 0, a bunch of those terms kind of disappeared, and we get just 1. So f of 0 is equal to 1, which means we could plot the point 0, 1. And then you could certainly plug in a value of 1/2. So that's the idea of plugging in some numerical values into a function. I want to go down to number 4 here because we're doing something interesting. We're not just replacing our x values with numbers, we're replacing our x values with expressions like t plus 1 and x plus h. Let's see what the result of that is. Now I don't really have room to do all of my work here, so I'm going to take this problem and bring it up here and work on it here. F of t plus 1 equals, now remember, I've just replaced this x value with a t plus 1. So I'm going to replace this x value and this x value with a t plus 1, and you can bet I'm going to be using parentheses. So this equals t plus 1 in parentheses squared plus 3 times my new x value of t plus 1 in parentheses, there we go, and then with a minus 2 at the end. Now be careful. When it's time to square this t plus 1, that does not turn into t squared plus 1 squared. If you need to, you should write this out as t plus 1 times t plus 1. That's what it means to square something. And then we can distribute the multiplication by 3, giving us 3t plus 3. And then I'm going to leave the minus 2 at the end. We'll deal with that on the next step. So in going from this line to this line, really all I did was distribute. I did write out the t plus 1 times t plus 1, but we haven't really done any arithmetic yet. But the next big thing that I'm going to do is I am going to FOIL the t plus 1 times t plus 1, and I think I'll combine like terms down here. So I'll write FOIL and combine like terms, CLT for combine like terms. Alright, foiling gives me a t squared plus t plus t plus 1, and then we have the plus 3t and a plus 1 from combining like terms. So just so you're clear on where all of those new elements came from, I suppose we could make that a little bit larger. There we go. And then the last thing that we need to do is combine like terms one more time. I'm going to get rid of those bubbles because they're confusing me. I guess I'll come down here and write equals. Now how many t squareds do we have? I think there's only this one instance of t squared, so I will write down my t to the largest power. And then let's look for t's, t to the first power. Here's a positive t and another one, so now I've got 2 t's plus another 3 t's for a total of positive 5t. And then we'll look for our constant values. I see a plus 1 here and a plus 1 there, here a plus 1, there a plus 1, for a total of 2 plus 1s. And so this is t squared plus 5t plus 2. This is f of t plus 1. It's the result of having plugged t plus 1 into our function f. And you could go through similar motions plugging in an x plus h. X plus h is an expression that we plug into various functions well into our study of mathematics. You would plug in an x plus h in an intermediate algebra class. You'll do it in college algebra. You might not do it so much in a pre-calc class, but definitely in a business calculus class or a calculus 1 class. So if either one of those are part of your track, be aware that plugging in expressions like x plus h into a function will be an active part of some of the math that you're going to see coming up. Number 5 is a little different. We're going to use this graph on the right in order to answer some questions, and the first question, part A, says what is f of 1? And if we go into the graph, remember that f of 1, that 1 is an input value, which makes it an x value. So let's go over here and find where x equals 1. There it is on our x-axis. And if we go up to our function, we arrive at this point. And what is the corresponding y value at the point where x equals 1? That looks like it's a y value of 2. So we come back over here and we say that f of 1 equals 2. It equals 2. F of 1 equals 2 is telling us a lot of things. The domain value of 1 has a corresponding range value of 2. F of 1 equals 2 means that there's a point that we could plot somewhere that has coordinates 1, 2. It's an input value of 1 and an output value of 2, so we can say that a bunch of different ways. Let's go down to part C first. Part C says, for what numbers x is f of x equal to 2? So instead of giving us an input value, they're giving us the output value. So we have to find where does y equal 2. Well, here's a y value. This is on the y-axis. That's where y equals 2. And if we move horizontally from there to the right, we arrive at this point. That point on our blue graph has a y value of 2. And if we had gone to the left, we slide over to this point, which also looks like it has a y value of 2. And what are the x values that correspond to those 2 points? It looks like an x value of -2 and an x value of +1 have corresponding y values of 2. So the answer to this question, let's read the question one more time. For what numbers x is f of x equal to 2? The answer to this would be an x value of -2 or an x value of +1. Both of those x values corresponded to a y value of 2. In other words, f of -2 equals 2, and f of +1 is equal to 2. The way that you present this answer, -2 and 1, could vary. You could see it in set braces like that. You could just have a text entry box in an online homework assignment and you type in -2, 1, and that's it. In a multiple choice situation, maybe you just see those 2 numbers, maybe you see them in set braces. You will not see them written like this. This has other meanings. This is not a list of 2 numbers. This is a list of 2 numbers, or perhaps just this would be a good list of 2 numbers. So you'll see it one of those ways, but not like that. And then part B says, is f of 40 positive or negative? And let's think about what that means. 40 is an input value, which makes it an x coordinate. And they're saying, what is f of 40? Let's go back over here. This says f of 1 is, right, the equal sign means is 2. And we said that the 1 was the input value and 2 was the output value. Is f of 40 positive or negative? If I were going to answer that question with a sentence, I would say f of 40 is, right, is, and they want to know, is this number over here going to be positive or negative? Well, with 40 as an input value, which is an x value, they're asking us, is this y value over here going to be positive or negative? Well, somewhere on our graph, I sure hope there's a point that has coordinates 40, something, and I hope I can tell whether that something, that y value, is positive or negative. Let's go have a look. Now 40 is not on this graph as an x coordinate. Our x values are only demonstrated here going out to +5. But it looks to me like this line keeps going down and to the right. Our graph keeps going down and to the right. And the farther to the right it goes, the farther down it goes. All of these y values down here are negative, and as we continue going down, they're going to get more negative. So I would say that if we went so far out to the right that we found an x value of 40, that our graph is going to be way down there, well into the negatives. So I think it's safe to say that f of 40 is negative. The corresponding y value would be negative. We've talked about domain and range in the previous section. I've mentioned it a bunch of times already in this section. Domain, that's the group of input values, the x values, and range is the group of y values or output values. And this is a little subsection that's all about domain of a function. And in order to find the domain of a function, it's being recommended that we keep some things in mind. We want to exclude values of x that make the denominator of a fraction equal to 0, and we want to exclude values that make the expression within a square root negative, because we don't want to divide by 0 and we don't want to take the square root of a negative number. Are we allowed to take the square root of 0? Well, if I asked you for the square root of 9, you might say 3. And if I said why, or how do you know it's 3, you would say, well, 3 times 3 takes me back to the 9. So let's apply that to the square root of 0. What's the square root of 0? Or why don't you ask me what the square root of 0 is? My answer to you is 0. And then you ask me, well, how do you know that? And I say, because 0 times 0 takes me back to 0. So indeed, you can take the square root of 0, so that's okay. You just want to avoid taking the square root of a negative number. So let's go in and look at some of these different situations in a little more detail. Here we're given a function called f, and f of x is equal to negative 1 over x minus 7. And when I see that variable in the denominator, I know that I've got to be careful. And what I need to avoid, or what I need to realize, is that there's so many different ways to say this. Instinctively, some of you are looking at this and saying, well, x can't equal 7, because if I change that x into a 7, then in the denominator I've got 7 minus 7, which equals 0, and that's division by 0. I can't have a 0 in the denominator, so I better avoid an x value of 7. That's a great way to think of it. I like that because it's maybe the most common sense way to think of it. Now this is nice because that x value of positive 7 kind of jumps out at you as being problematic. Another way to state it a little bit more formally is to remember that generally speaking, you want for your denominator to not equal 0. And if I solve this statement by adding 7 to both sides, I get this statement that says x is not allowed to equal 7. So there's a more algebraic way to arrive at your conclusion that x is not allowed to equal positive 7. Great. Then this question says write the domain in interval notation. Well, how do I do that? How do I write this in interval notation? You're not going to. The domain of a function is a list of x values that you are allowed to plug into your function. So somehow we have to give a list of all of the x values. Negatives, positives, 0, square roots, all of the decimals, all of the fractions, right? All of the numbers on the whole number line, decimals included, except for the number 7. So I'm going to say that my domain, the list of x values that I am allowed to use, starts on the number line all the way down at negative infinity, and I could shade that number line all the way up through 0 to positive 7, but I'm going to exclude the value of 7 by putting this open bracket on it here. Or, and this is the union symbol, or we could choose values starting at positive 7, but again excluding the value of 7 with our open bracket, and I could keep shading my number line all the way up to positive infinity. And remember that positive and negative infinity both take open brackets, always. So this is the answer that we're looking for. You wouldn't put in this D with a colon on it, probably. You'll just type this stuff into a text entry box in an online assignment, or as a multiple choice question on a quiz or a test. You would probably just see that notation. All right. Visually, I like to look at it on a number line. If this is the number 7, I would have an open circle at the number 7, because we don't want to include 7 in our domain. And then I could shade the entire rest of the number line all the way to the left and all the way to the right. So this would be your solution if you were asked to graph the domain for f of x. Let's keep going vertically here. What about number 8? Write the domain in interval notation. This function, notice, is called h, so we've got functions of different names. H of x is equal to x squared minus 9, is there any danger of division by 0 in this function? I don't see any division at all, so I don't have to worry about that. What about any danger of square rooting a negative number? Well, I don't see any square root symbols, so I don't think there's any danger there. There's also no natural logs, there are no variables in the exponent position, there are no trigonometric functions like sine, cosine, and tangent, so wow, I don't think there's anything to exclude. I think we can put any number we want to. We can put in any number we want. Can I square a negative number? Sure. Can I take 0 and multiply it by itself? Can I square 0? Yeah. How about a positive number? Absolutely. This function, which is also called a polynomial function, doesn't have any restrictions. So its domain is all real numbers. Or, using interval notation, we'll go from negative infinity up to positive infinity. Or this could be represented with this interesting looking capital R that represents this set of all real numbers. Alright, or it might just say all real numbers. Again, this is a polynomial. If you're taking notes on this, it's a poly, P-O-L-Y, nomial, N-O-M-I-A-L. Polynomial functions have domains that are the set of real numbers, all real numbers. No danger of division by 0, no danger of square rooting a negative number, so you're in the clear. And then let's look at number 10. We've already seen a situation where we had to avoid division by 0. Here we have a situation where we need to avoid square rooting a negative number. How do we prevent that from happening? I'm going to write down, now in number 6, the very first thing that I wrote down was what I didn't want to happen. I didn't want x to equal positive 7. In this problem, I'm going to write down what I want. I want x plus 5, the radicand, the stuff under the square root symbol. I want x plus 5 to be greater than or equal to 0. Again, we can take the square root of 0. We can take the square root of a positive number. So that's what I'm trying to make happen here. And if I subtract 5 from both sides of this inequality, I find that x is greater than or equal to negative 5. So this is our domain. All of the x values that are greater than or equal to negative 5. Don't worry about the fact that we're using an x value that's negative. It's that we don't want this to be negative. So this plus 5 right here has us covered. So this is one way that you could present your domain. You could present it using set builder notation, which would be the set of x values such that x is greater than or equal to negative 5, but we were not asked to answer using set builder notation. You could graph all of your acceptable domain values, starting from negative 5, including negative 5, and shading all the way to the right. That's where all of the x values are that are greater than or equal to negative 5. Instead of using the closed circle or the colored in dot there above the negative 5, you could use our new notation, which would be an closed bracket or a square bracket. This would be an acceptable way to graph your domain, but we were not asked to graph our domain. We wanted an interval notation. So let's finally put it in interval notation. We're going to include the value of negative 5 as an acceptable value, and that shading on the number line goes all the way up to positive infinity. That's where all of the x values are that are greater than or equal to negative 5. That is your domain, so let's finally put a box around that one. And those are the scenarios that you really need to watch out for. Avoiding division by 0 and avoiding square rooting a negative number. What's happening on this side of the world? Number 7 also has a variable in the denominator, so we know we need to be careful there. We want x squared minus 4 to not equal 0. And if I add 4 to both sides of this does not equal equation, I get x squared is not allowed to equal positive 4. Well, what x values could I square that would cause me to have a value of 4? Well, certainly 2 squared would equal 4, so I want to avoid an x value of 2. Check this out. Take a 2, plug it in there, square it, you get 4. Minus 4, 0. Division by 0. Not good. What else? If we square root both sides of this statement, we get x does not equal, and then what's the square root of 4? Careful. The square root property says the answer is plus or minus 2. So we want to avoid x values of both positive and negative 2. Negative 2 squared would equal positive 4 minus 4 division by 0. Alright, so let's take this and write it as a domain in interval notation. The list of x values that we are allowed to plug into our function. That is any of the x values from negative infinity up to negative 2, excluding the negative 2 with an open bracket, or we can use the values between negative 2 and positive 2, but excluding negative and positive 2 again with the open brackets, or we could use x values that go from 2 all the way up to positive infinity with an open bracket on the 2 and on the positive infinity. Positive and negative infinity, always taking open brackets. I'm going to probably say it every time. You're never going to forget that one. And that would be your domain, so you can put a box around that. That's quite the interval notation. Remember that the U means union. It is joining those 3 intervals together in order to turn them into one larger collection of acceptable x values that make up our domain. In number 9, I see the variable in the denominator also, which tells me I need to be careful. I need to make sure I avoid division by 0. If I take a number and I square it, I'm going to get a positive number, unless the number I'm squaring is 0. So I could get 0 or a positive number. And when I take 0 or a positive number and I add 9 to it, I'm definitely going to have a positive number. So there's no way for this denominator to be 0. At its absolute smallest, it's going to be equal to 9, that denominator. So there's no danger, actually, of division by 0. We have determined there are no restrictions on our x value there, because you can't find an x value that would cause division by 0 in that fraction. Therefore, the domain is all real numbers, or using interval notation, negative infinity to positive infinity. And in number 11, we'll have this be our last example of avoiding the square rooting of a negative number. Again, we want to make sure our radicand of 2 minus 4x stays greater than or equal to 0. Add 4x to both sides. Divide both sides by positive 4. And that's your domain. All of the x values that are less than or equal to 1/2. On a number line, here's the 1/2. X values less than or equal to it would be shading to the left. And in interval notation, read that shaded region from left to right. How far to the left does it get shaded? All the way down to negative infinity. And how far up does the shading go? All the way to 1/2. And are we including the value of 1/2 in our domain? We are, because this closed circle was the result of having an or equal to sign here, which means we could have used a square bracket, which means for sure we're going to use a square bracket in interval notation. That, ladies and gentlemen, is your domain. That is a very in-depth conversation about functions. It was a lot of information, so go back and watch little bits and pieces of that and take these example problems with you and use them as some templates as you attempt your homework assignment, and be having that conversation in your head and thinking about what it is that you're actually trying to achieve as you look at these domain questions. And as you're using function notation, always be mindful of the fact that you're working with input and output values, which are x and y values, which make up your domain and range. X, Y, input, output, domain, range, left, right, salt, pepper, black, white. We say these things in a certain order traditionally, and they match up very nicely. X, Y, domain, range. Okay, good luck. See you next time.